Hi guys, my name is Samuel Jasper. I'm from CSC department. My topic for mathematics for computing is on locally finite graphs with ends, a topological approach, and basic theory. Uh, let's get into introduction. A locally finite graph with ends is an infinitely large graph where every vertex has a finite degree, combined with the topological concept of ends that represent directions or ways to escape to infinity from the finite part of the graph. These ends are treated as topological points, allowing for creation of a compactified space by adding the ends to the original graph, which enables topological analysis of infinite structures that can be done with finite graphs. Let's see what this finite graph is all about. It is a completely contained with only finitely many vertices and edges. Tools like shortest path, cycles, connectivity, and spanning trees apply directly. Proofs often rely on finiteness, for example, induction, compactness within the graph itself. Let's see what is infinitely locally finite graphs is all about. Infinitely local finite graphs are the graphs which extend endlessly, but each vertex connects to finitely many neighbors. New phenomena appearance is done by infinite race, which is a path that never ends, and loss of compactness, which arguments that rely on finiteness breakdown. In finite graph theory, classical tools work because the structure is bounded and manageable. When graphs become infinite yet locally finite, new complications arise. Rays extend indefinitely, compactness arguments collapse, and cycles may involve directions at infinite. To address these, digital introductions introduces the concept of ends, which acts as boundary points capturing how rays extend. By adjoining these ends, and finite graph gains a compact topological structure that restores many finite-like properties. This transformation is essential for extending well-known theorems to the infinite case, making ends a certain tool in the theory. Key concepts: locally finite graph. Definition: a graph where each vertex has finite degree, only finitely many edges incident to it. For example, an infinite grid Z into Z is locally finite because each vertex connects to exactly four neighbors. Non-example: a star with finitely many leaves leaves is not locally finite since the center vertex has infinite degree. The importance is local finiteness ensures that while the graph may be infinite, its local neighborhoods are manageable. Ends of a graph. An end is an equivalence class of infinite rays. Infinite rays are the one-way infinite path. Two rays are in the same end if for every finite set of vertices you remove, the tails of both rays lie in the same component of what remains. Intuition. Ends represent directions to infinity. For example, an infinite line like Z has two ends, left and right. An infinite binary tree has uncountably many ends since each infinite branch represents a unique direction. Topological arcs and circles. Arcs. It generalizes finite path how but now allowed to pass through ends. Circles. It is a generalized cycles which can be finite or infinite, includes ends. The importance is these structures let us extend finite cycle path theorems like cycle spaces connectivity results to the infinite setting. Key concepts in digital framework ensure that infinite graphs can be studied rigorously. Locally finite graphs restrict vertex degrees, making them tractable. Ends capture infinite directions by grouping rays that cannot be separated by finite cuts. With ends, we can define topological arcs and circles, extending finite notion of path and cycles to infinite cases. Finally, compactification transforms the graph into a closed, compact topological space, restoring powerful finite style arguments and enabling extensions of classical graph results. Contributions of Part 1: Rigorous definitions. It introduces ends, topological arcs, and circles formally. It sets up a consistent vocabulary for infinite graphs with ends. It clarifies equivalence of rays and connectivity concepts in infinite settings. Extension of finite results. Many classical finite graph theorems are generalized by paths and cycles and connectivity theorems. Paths and cycles now include ends. Connectivity theorems like Menger's theorem extended using topological tools. Infinite graphs can now be analyzed in a finite-like framework. Survey of proof strategies. It discusses techniques for infinite graph. The techniques are compactness arguments via ends, handling infinite paths and cycles, avoiding pitfalls that arise when fitness is assumed. Connect, Connections to other fields. Algebraic topology. Using ends and compactification to define homology and fundamental groups is known as algebraic topology. Matroid theory. This matroid theory is known for infinite matroids related to cycles in infinite graphs. Bridges combinators with topology and algebra. Part 1 of Digital Survey lays the groundwork for infinite graph theory by providing precise definitions, formalizing ends, and establishing topological concepts like arcs and circles. It shows how classical theorems from finite graph theory can be meaningfully extend to infinite graph. The paper also surveys proof strategy specific to infinite graph, highlights connections to algebraic topology and matroid theory, and lists open problems to guide future research. Collectively, these contributions make Part 1 an essential reference for anyone studying infinite locally finite graph. The survey series is structured to gradually introduce the reader to the topological study of infinite graphs. Part 1 provides the foundational theory, defining ends, topological arcs, circles, and compactification. Part 2 of theory demonstrates applications by extending finite graph theorems such as conductivity and cycle results to infinite graphs using these concepts. Part 3 delves into algebraic topology, describing the fundamental group and homology of compactified graphs. Together, the series provides a coherent framework connecting combinatorics and topology, equipping research to study infinite graphs rigorously and systematically. Significant unified framework. It treats finite and infinite graphs under the same topological perspective. Hence, allow infinite graphs to behave like finite ones in key respects. For example, infinite grid graphs can now be analyzed for connectivity and cycles similarly to finite graph. Extension of classical theorems. Many well-known theorems from finite graph theory now generalize naturally. Menger's theorem applies to connectivity between ends and vertices. Cycle space theory includes infinite cycles through ends. Eulerian and Hamiltonian graph conditions can be redefined for infinite graphs. Bridging compactories and topology. Distal's approach introduces topological tools into combinatories. Compactification of graphs, arcs, and circles as topological paths and cycles. Used of continuity and compactness in proofs. It is an inspiring research where They open problems in part 1, guide further exploration in finite graph theory. It provides a rich playground for combinatorial, topological, and algebraic studies. Encourages interdisciplinary research bridging graph theory, topology, and matroid theory. Applications of the topological approach. It is used for extending classical graph theorems like Menger's theorem cycle spaces. In Menger's theorem, it for finite graphs only. Now it is connectivity can be studied between vertices and ends or two ends. Uses ends to define infinite disjoint paths, preserving the essence of the theorem. Cycle spaces. Finite cycle space, all cycles in a finite graph and infinite graphs include finite cycles passing through ends. Topological methods for infinite graphs. Arcs and circles allow generalized connectivity analysis studies of infinite paths that loop through ends, defining new topological invariants in graph. Structural insights. Identify end-dense regions or directions with high connectivity. It studies topological embedding of infinite graphs in surfaces. The topological approach enables the extension of classical theoretic results to infinite locally finite graph. Menger's theorem, cycle spaces, Eulerian and Hamiltonian properties and connectivity results can now incorporate ends, giving rigorous meaning to infinite paths and cycles. Topological arcs, circles, and compactification allow proofs and arguments to generalize naturally. Conclusion. In conclusion, Part 1 of Digital Survey lays the foundation for comprehensive theory of infinite locally finite graphs. By introducing ends and the concept of compactification, infinite graphs acquire a structure that allows infinite graph techniques to be applied effectively. Topological arcs and circles extend classical notions of paths and cycles, while compactification ensures that connectivity and other properties can be studied rigorously. The key concepts that we discussed are ends are central to handling infinite direction in graphs. Topological arcs and circles generalize paths and circles. Distance framework introduces ends and compactification, transforming infinite graphs into topological spaces. Thank you.